Okay, so welcome to this video on binary numbers. This is the second video for the course, and this video has about 30 slides or so. I'm on an iPad now, actually, instead of on the laptop, just because I'll be doing a lot more writing in this video. So the writing comes in a little clearer on an iPad. So I'll be using that, and we'll be doing some computation, I guess, more so in this video than in last week's. So you might especially want to have a notebook with you so that you can, as usual, take notes, but also maybe to do some of the computational problems along with me. So first, just a quick reminder of a couple things from last time. So we sort of finished the last video thinking a little bit about segueing into this topic, which is binary data or binary things. So just as a reminder, the word binary is just a word that really means you have two options. Bi meaning two, and it can be interpreted, or it occurs to us sometimes in data form, which is what we're going to spend some time talking about right now. And I think there's maybe some common knowledge out there that every thing that might be stored on a computer, any data that you have, is actually stored in binary form. So today we're going to talk more about, well, what is a binary number? What does it mean? How do we reconcile that with our numbers, our sort of regular number system, and so on and so on. So anyway, but just as a reminder, right, in trying to think about, well, how could I store data? We had the idea of digital data and analog data. Analog data is very complicated. You have many possible values. You could think about that as a dimmer switch on a light that gives you, in theory, sort of infinity different light settings. Compared to digital data, and in particular the simplest digital data, which is binary, which just gives you two options. If you're thinking about it in terms of a light switch, you might think about it as on or off. And if you're thinking true and false is sort of also a good way of thinking about it. And if you're just thinking about a number and saying it's binary, a number could be binary, we might just say it's either 0 or 1, meaning, those are the only two options that you might have, which of course in our number system we have a lot more options. But we'll examine that in this video, as how to kind of think of numbers as just being made of zeros and ones. Okay, and the long range idea of this is that anything that we might have, even something like the video you're watching right now, is actually, I'm not kidding, made up of binary numbers, zeros and ones. Obviously there have to be a lot of them in order to distinguish this video that you're currently listening to and some other video. So there's a lot that goes into, of course, capturing things like visual images and sound and things like that, and we'll get to that later. So the other side of binary is that in addition to it being the system that we use in order to store things, it's also actually the system that actually physically powers a computer or any sort of electronic device. And it does so in the same sense that you have circuitry in a computer. I think we all kind of know that. And what it is it's a path of electricity. Without getting into too complicated details, I think we know electricity sort of flows maybe across a wire, and if you break the wire, then the electricity doesn't flow. In other words, if there's a gap, then we would maybe say that's off. That's how a light switch works, right? So a light switch that's in your home is when the switch is down, meaning the light is off, the circuit, the wires are broken. In other words, they don't make a complete circuit. And then you can flip the switch on, and that connects the wires, and the light bulb turns on. And that's it. Those are the only options you have. Again, binary, just two options. And this is also how a computer actually moves, you might say, or does things, or makes things move. and makes decisions happen is with a very, very, very complicated circuitry of these little light switches, or sometimes called transistors. So we'll talk a little bit more about the binary aspect of the circuits a little bit later. So, but to think just a little bit more about data and how data might be stored in binary, I asked you to do this exercise last time, which is to think of maybe light bulbs and thinking about them as being either on or off. So in particular, I asked you to think about if you had 3 light bulbs right here, and we were trying to figure out, making codes, so to speak, right? So something very sort of Paul Revere, 1 if by land, 2 if by sea sort of modern take on that. But if I'm trying to convey to you a code, and I have 3 light bulbs that I can obviously turn them on or off, and those are my only options, is there a way for me to convey a code or a number to you, and how many in particular, how many different codes could I convey to you with 3 light bulbs? So this is from last time. So let me advance to the answer, which you saw last time. So in trying to sort of consider what could I have, or what might I, what sequences or what codes might I send, sort of the maybe base code or the where to start might be to turn all 3 bulbs off, in which case I might say, off, 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 or maybe even I could think about that as, 0, 0, 0 to say that all 3 are off. And that's probably a code, right? Maybe that's a code for, I've got nothing right now. And then if I go through this and try to say, well, okay, so what could I do in terms of turning them off and on? Hopefully you explored a little bit and came up with, at least mentally, some sort of a picture like this one right here, which has, sorry about that, which has 8 different combinations. You can see them all right here in the chart, of offs and ons that might correspond to the 8 codes. If I use 0 for off and 1 for on, might correspond to these numbers over here, or these expressions, I guess, over here. And indeed, there's 8 different codes that I could send that hopefully, assuming we're secret spies or something, have some meaning to you when I send you, that code of first light bulb on, middle light bulb off, second, last light bulb on, that you say, oh, okay, that means I'm supposed to whatever, okay? So, but the point being, right, the connection here is that for 3 lights, for 3 bulbs, you could make 8 unique codes or 8 unique sequences of ons and offs, or you could say zeros and ones. All right. And I think in the homework I asked you to consider what about if you had 4 bulbs? And I think the connection here was that, right, so if we had 3 bulbs, if I had 3 bulbs like we see in the picture here, I was able to make, we could make 8 codes or 8 sequences up here. And I think I asked you in the homework to answer the question, what if you had 4 bulbs? And hopefully, I think most of you got this. You said that meant we could do 16 codes. And in fact, I should have maybe filled in sort of the easier case that if you have 2 bulbs, that one's pretty easy to see, I hope. You could either have them both off, both on, or the first one off, and the second one on, or the second one off, and the first one on, right? So I think that's only 4 different sequences, right? So, and obviously we could keep going with this story, but hopefully there's maybe something you're noticing as I increase the number of bulbs. Maybe you're noticing, hopefully, something that is happening with these number of codes. So I won't spoil the surprise because I'll write that down for you shortly. But indeed, as I promised, it's kind of hard to think about or hard to imagine. But everything that you might have, any data you have stored, any program that's running on your computer, even things that are complicated like video or pictures and sounds, songs you've downloaded, an essay that you wrote for a class, a photo, everything you've got that's data is stored as zeros and ones, which is kind of crazy, right? Again, how is like an amazing sort of feat, and that this technology really occurred in the last 50 years or so to be able to do this efficiently is kind of amazing. So we'll get to how to actually store things like pictures and like sounds after we get a little bit better familiarity with this just sort of system of what is binary, what are binary numbers. All right, so here's where we start really with this week's material. So first of all, let's use all the official terms here. So when we talk about a single data location, you could say, in memory, you've heard this term before, I think. We call that a bit. All right, so a bit, which is just literally the abbreviation for binary digit. If you cross out all of those letters, you get bit, right? That's where it comes from. It's just that it's a shortened version. And all it means is that a bit, right, or what is a bit? It's a memory location where you can either put a 0 or a 1. And that's it. And I promise whatever device you're watching this video on is full of millions and billions, maybe even trillions, of bits, of little locations that can either have a value of 1 or a value of 0 stored in each little spot. So it's a little hard to imagine because, of course, there's so many of them. So it's kind of hard to even visualize it. But this is what sort of nanotechnology is all about, is that we can do amazing things in reasonably small spaces. Your cell phone, for example, has billions of little spots, I guess you could say, which are zeros or ones, which are ready to hold zeros or ones, and can flip from one to the other almost instantaneously in order to do things like save things or transmit text messages or things like that. So anyway, but a bit, right? A bit is just a little memory spot. You could sort of almost visualize it as a little box in memory that inside of that box we could either see a 0 or we could see a 1, and that's all it is. All right? And any computer or electronic device's memory is just a whole bunch of these little boxes that are currently and forever will hold zeros and ones in some sort of order. All right, so, and again, you could think about this as light switches being on and off, or zeros and ones, which is more of how we're gonna think about it. Now, as you might imagine, the sequences of these numbers, the placement or location of them also conveys a certain amount of meaning. And I'll show you what I mean by that. So let's first make sure we're all clear, right, that the examples we've talked about so far could be translated into, with light bulbs that is, could be translated into binary numbers. And by that I just mean that I might think about the light bulbs being off as zeros and the light bulbs being on as ones. And so this sequence of light bulbs I might think about corresponding to that binary number. Okay? And a binary number is just a series of bits, just a bunch of bits, which we typically group into eights. So an 8-bit binary number, something like this, 0001, 0001, 0001. This is what's known as a byte. So I don't know why it's not on here, so I will write it in for you here, right? Or maybe I'll put it at the bottom here, right? So a group of 8 bits is called a byte. Okay, so the number up here depicted in light bulbs or with the zeros and ones, right? So we might imagine that somewhere in memory, I've got 8 bits here. So let me draw them out for you. Right, so I've got 8 boxes in memory, and if it's currently holding the light bulb number up there, then currently those numbers, that sequence of zeros and ones, might be stored in these 8 boxes, and collectively this whole thing together is called a byte. Right, so a byte is this group of 8 bits that are sitting next to each other comprise a byte of memory. Okay, so what else to say about this? So, well, this number, of course, has 6 zeros and 2 ones. But of course, they're in different, the location of where they are should have some sort of meaning. In other words, if I take these zeros and ones and rearrange them, I think that probably has some new meaning. And we saw that in the examples with the light bulbs earlier, right? That you can maximize your number of codes if I considered maybe, turning this bulb off and this bulb off, and I turned maybe this one on and this one on. I'd still have 2 on and 6 off. But that's probably a different code, right? Again, the idea is that a person looking at it would say, oh, okay, they turned the first one on and the next to last one on. That's different than when they turned the last one on and this one on. Okay, so the location or sequence also has some meaning to the number. And that shouldn't seem super weird, because if we think about our number system, we all know this, we learned this one in elementary school. We use, of course, 10 numerals, we might call them, or symbols, are familiar to all of us, 0 through 9. And when we look at a number in our number system, maybe the number 454 or 454, of course, this is made up of 2 4s, but the 4s that are in this number have different meanings because they're in different positions. So I know I'm hopefully not telling you anything new here, right? But this 4, the first 4, corresponds to 4 hundreds. And the second 4, of course, corresponds to 4 ones, right? They have very different meaning. If I say you have 400 things, that's different than saying you have 4 of them. And yet the numeral 4 is identical, whether it's in here or here. Okay, but this is all familiar to us, right? We know that of course that's true. We know, of course, the location makes a difference in terms of how much is that numeral worth. Similarly, the order of the numbers also makes a difference, and by that I just mean that we definitely have a difference between the number 454 and the number 544. These are both, of course, very different. Even though they're made up of the same numbers or numerals, they convey different meaning. Okay, so this is all hopefully very familiar from, second grade or whenever we might have learned this. But I'll ask, so as I sort of broke this apart into how much are these digits worth, so to speak, I used the what I think we called place values before, ones, tens, hundreds. And if you learn math nowadays, many of us maybe learned math in a sort of traditional way. Now they spend a lot more time focusing on teaching math as, thinking about, well, how much are all these things worth? So we're sort of going back to that notion and saying 545, which I'll try not to call that 554. I'll just try to say 545 is really worth that much. And which we know, of course, yes, that's 554 things, whatever this is counting up. All right. Now, what's so special about, of course, these place values, right? So namely 1, 10, 100, 1,000, and so on. Well, hopefully you remember that these are the powers of 10. Right? In other words, remember, any number to the 0 power is 1. So the 1, as we said in elementary school, the ones digit is really 10 to the 0 power. And then the next digit in our numbering system is the tens digit, as we called it. And just a reminder, anything to the first power is itself. So 10 to the first, of course, is just 10. Okay, and then we're more familiar with the idea that 100 is 10 squared, and 1,000 is 10 cubed, and so on and so on and so on. Okay, so now that's our world. So let's pull this all together and describe our numbering system, our normal everyday numbering system, which is called the decimal system, or the decimal numbering system, or it's also called the base 10 system. So decimal, dec means 10, I think, in Latin. So this is all saying the same thing. So what's special about our system? It's very familiar to us, so sometimes it's hard to kind of pretend that we don't know what it is, I guess. So try to forget as much of first and second grade as possible and pretend I'm explaining this to you the first time. What are the sort of hallmarks of our numbering system? Well, we use 10 symbols, which shouldn't be a surprise because we're using a base 10 system. So we'll see 10 all over the place in this slide. But anyway, we use 10 symbols. And of course, we know them to be the numerals or the digits, you could say 0 through 9. There's 10 of them. We don't use any more than just those 10 symbols, right? Even when I write a large number, it's just made up of zeros and 0 through 9s, right? So these are the only actual symbols, or the only characters, I guess, that are in our base 10, or our decimal number system, and there are 10 of them. And in fact, we use 0 through 1 less than 10. Okay, so there's going to be lots of parallels here. And one more instance of the number 10 appearing in our lives is what I reminded you of on the last slide, which is that the place values, or the positions of the digits, correspond to the powers of 10. So this should look somewhat familiar down here, which is to say that I know that the ones digit, as we call it, right, is the 10 to the 0 power, and then the tens digit is the 10 to the first, and so on as I move to the left. And so when I think about a number, which I won't say it, but I'll call that the number 1428 in our system, 1428, I know I translate that and I say, oh, well, this 1 is worth 1,000, and then this 4 is worth 4 hundreds, and this 2 is worth 2 tens, and this 8 is worth 8 ones. And so when I think about that quantity, how many beans is that? Okay, I have a visual image of, well, a lot of beans, I guess, right? 1,428. All right. So obviously, this is hopefully all very routine. So now we have to try to say, all right, well, we speak base 10, right? That's our world. That's our decimal number system, also known as base 10, and all of the stuff that goes along with that we're all experts in. So now we have to sort of play the game of, well, a computer, any computer, the computer does not speak base 10. Now you might say, well, there's numbers on the keyboard that are 0 through 9. That's true. And, I'm sure you can punch into a calculator in a computer or on your phone, and it seems like it's doing math in our world. But it isn't. I promise you, every single operation and every single data point and every single thing that's happening in a computer is binary. That is the only lingo, or that's the only language that the computer speaks. Now it interfaces with us so that we don't have to speak its language. But since we're trying to understand better how the heck this thing works, we should try to become sort of fluent in the computer's numbering system, which is the binary numbering system, also known as base 2. Okay, remember our system is base 10, and this is base 2. So remember, our system uses 10 symbols, 0 through 9. So base 2 system, the binary system, uses only 2 symbols, and they are 0 and 1. Again, same idea. We use 10, 0 through 9, which is 1 less than 10. Binary system only uses 2 symbols. Okay, so those 2 symbols would be just, well, 0 and 1, which it should sound familiar, right? This is what we've been sort of setting ourselves up for, is the idea of it's on or off, or it's true or false, or it's 0 or 1. All right, and so since our system uses powers of 10, because it's a base 10 system, it should hopefully make sense that the binary system uses powers of 2 as its place values. Okay, so each position is a multiple of 2, right? In other words, you just double it to get to the next place value, and so on and so on. All right, so for example, a 4-digit number, now I really will just call it 1001. Don't call that 1001, because as we're going to see in a moment, it's not equal to that. The numeral, the binary number 1001, if I want to know, well, how much is that? How many beans is that? I say, okay, well, the number 1001, let me see. So it's binary, which means the place values are the powers of 2. So I might say, okay, so the first place value is the 2 to the 0 digit, or you could say the 1s digit. So that's just like our system. But now the next place value is the 2 to the first power, which is 2, right? That's 2. So the next digit, which in my number happens to be a 0, is the 2's digit. Okay, I go to the next place value, and now that's the 2 squared, or we would call that 4. So this 0 that's here is in the 4's place value, or in other words, it's how many 4's do I have. And then lastly, the next place value is 2 cubed, which of course in our world is 8. And so the place value that's there, the digit that's there is worth 8. So if I try to consider this number in binary, 1001, and try to translate this to our world, I would say, well, this 1 is worth 8. This 0, which is none, right? I don't have any, but they'd be worth 4. This 0 is worth 2, which I don't have any of those either. And this 1 is worth 1. And so if you add these things up in our world, I think you'd get 9. Our number, I put it in quotes there just to say, right? 9 doesn't exist in binary, but as a concept, a quantity of 9 certainly does. So you might be saying, well, gee, in our world, right, so this quantity of 9, which we know what 9 means, right, in binary is written that way, and in our world it's written that way, right? So they mean the same thing. If I tell a computer to find me 1001 bits, it would find me 9 boxes. If I say to a person on the street, find me 9 pennies, he's going to give me, hopefully, maybe, 9 pennies, right? In any case, both of them know the binary system. The computer knows how many that is, and we know how many that is. The point is, it's the same thing. It's the same quantity, just written in 2 different number systems. So you could think about, 9 is English, and 1001 is Spanish, maybe, right? So they mean the same thing. They just are written in a different language, so to speak. All right? Now you might say, well, gee, isn't our system better? Because 9 is way easier to write than that. And in this case, I might have a hard time arguing with you that our number system doesn't perhaps seem a little more efficient. But we'll see. We'll explore sort of the pros and cons of our world versus the binary world. So let's get our feet wet with trying to do some conversions. So a good chunk of the skills, I guess, from this video are of the format of just trying to get us all familiar with thinking binarily. That's not probably a word, but thinking in binary. So let's do some conversions in order to just get the juices flowing with how might I try to translate back and forth maybe. So we'll start with the easy direction first, which is to convert a binary number, which you see a couple examples right here. I want to try to convert those to a base 10 number or a decimal number. In other words, one of our numbers. So tell me, how many is this and how many is that? Okay. Then we have a couple of other follow-up questions. If I have 6 bits, right, so 6 zeros and 1s at my disposal, what's the biggest number I could make in our world? And then also maybe tell me the range of numbers and how many different ones I could make. And maybe just as a last question, if you needed 1,000 different codes, how many bits do I need in order to do that? So these are some good questions to think about, and of course you'll see similar questions in the homework. So let's consider each of these problems, and we'll see what we can come up with. If you want to sort of be bold right now and try these, feel free to pause the video and try these questions on paper or somewhere off to the side, and then tune me back in or play me to see how it turns out. Okay, so I want to try to convert these 2 numbers to a decimal number, in other words, to one of our numbers. So let's start. There isn't really a whole lot of a strategy here, but I'm just going to try to get our thoughts organized here. And when I copy down the numbers, so we'll start with the first one here, I'm going to try to write them down with some meaning, right? So I'm going to, as I copy this down, let me say, all right, I've got the number 1 0 1 1 1 0. All right. And in terms of how much is this worth, I think the easiest thing to do is just sort of say, all right, well, these are all in some location, And if this was our numbering system, the way we speak this number already dictates the place values. But since we're in binary world, I don't know how much each of these is worth unless I probably maybe write it down. So I encourage you to maybe try it this way, especially while you're still getting comfortable with this. So it's always easiest maybe to start on the right. This is always worth, so the first digit in any numbering system is, as you remember, is worth 1, which I could say that's 2 to the 0, or that's worth 1, or that's the ones digit. Okay, now in binary, remember, in order to go to the next place value, I'm going to double, right? So I'm going to double, so that one's worth 2, or 2 to the first. And then I'm going to double again, so that one's worth 4, and I'm going to double again, so that one's worth 8, and this one's worth 16, and this one's worth 32. Okay, so just double, 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 or you could say these are all the powers of 2. And okay, so this is something that we don't need to do in base 10 because we kind of, it's built into our system. But for us to try to sort of convert to base 10, it's important for us to say, all right, how much are each of these digits actually worth? And now I just have a simple arithmetic question, which is to just sort of add these all up and see what I have. So let's see, if I try to add this all up here, I think I'd get, so this first digit, this 1 here, is worth 32. I don't have any 16s, so I mean you could write 0 times 16 if you want, but I'll just leave it off. This one is worth 8 from here. The next one is worth 4, and the next one is worth 2, and then I think that's it. So if I just do a little arithmetic in my head or on a calculator, I think I get that that's our number, 46. So if I want to say, if the computer is saying I have, 1011110 bits, in our world we would say, oh, you have 46 of them. Okay? So 46 should be the base 10 equivalent, or the decimal equivalent of that binary number. Okay, similarly, maybe we'll just quickly do this other one here. And let me jot it down first. So that's 1, 0, 0, 0, 0, 0, 1, 1. So this is a full byte of memory. This is 8 bits that you see here. Okay, and in order to know how much is all of this stuff worth, I'm just going to do the same trick that I used a second ago, which is to start here and say, well, I know the ones digit is always worth 1, and now since it's binary, I'm going to double. So 2, 4, 8, 16, 32. You're going to be so sick of, of writing the powers of 2 by the time we're done with this. But okay, so if I double, 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 double every time, I think that's where I end up, with the last digit on the left, or the first digit, I guess, being worth in the 128th place. So that 1 that's there is worth 128. Right? And then I don't have any of these. I don't have any 64s or 32s or 16s or 8s or 4s. So I'll just jump ahead to this guy, which is worth 2, right? 1, 2, and 1, 1. That last one on the end here is actually worth 1. And again, some pretty easy math here. I end up with 131 in base 10, or in our system. So this byte of memory, which is 1, 0, 0, 0, 0, 0, 1, 1, is actually our number, 131. Okay, and again, right, it is true, it requires more digits. This requires eight bits in order to convey a number that in our world we can convey with just three numbers. So, but anyway, we'll talk about that, as I mentioned, later. All right, so those are I think, hopefully 2 pretty easy first questions. So let's get to a little more interesting questions, I suppose, which is, tell me if we, let's say, just using 6 as our example, if I have 6 bits of memory, tell me maybe these things. Tell me what's maybe the biggest number. Maybe I'll also say what's the smallest number we can make, and how many different numbers can you make with 6 bits? Or how many different codes could I make with 6 bits? So I might say, well, all right, you're going to let me use 6 bits, so let me draw them out here. Okay, and since I'm thinking about place values, I might say that, again, that one's worth 1s, that's the 2s, the 4s, the 8s, the 16s, and the 32s. Okay, so maybe I could start with what's the smallest number that I could make, even though I didn't ask you to tell me. But just remember, even though I know it's a little funky working in base 2 instead of base 10, the same things, the same general ideas apply that exist in our world, which is if I say you're going to make a 6-digit number in our world, what's the smallest number you could make with 6 digits? I hope you would tell me something like, we'll put 0 in all of them, and that would be the smallest number you can make, and namely, that would just be 0. Right? So with 6 bits, I think, maybe the smallest number I could make would be the number 0, also known as 0, right? Or our number 0. Nothing. You got nothing. So all zeros, I think, might be the smallest number, and maybe the largest number. Well, so again, try to think about our number system. If I said you have a 6-digit number, and you want to make it as big as possible, in our world, you might tell me, oh, well, that's 999,999, right? That would be the biggest 6-digit number we could make in our world. And you would know that, or you would come up with that, because you would basically be trying to say, well, if I want to maximize each place value, put the biggest numeral I have in each spot, and that should add up to the biggest number I could possibly make with 6 digits. So I want to use the same idea here, which is to say, okay, so if I want to make the biggest number I could make in binary, I want to put the largest number I can in each spot. Well, remember, in binary, I have to use just zeros and ones. And so the largest number I could make is, I think, putting ones in each of the 6 spots. Okay, which again is the analog of doing this in our world. And if I do that, if I put a 1, 1, 1, 1, 1, 1, and I add up, just like I did in the last problem, how much is that number worth? 1, 1, 1, 1, 1, 1. If I add up these numbers, 1 plus 2 plus 4 plus 8 plus 16 plus 32, you can do it on a calculator or off to the side. I'm pretty sure you get the number 63. Okay. All right, so let's see. So where are we, right? So we came up with the answer to this question. 63 is the biggest number you can make. And I didn't ask you, but I'm including it at no extra charge. The smallest number you can make is 0. And hopefully use your imagination a little bit. You should be able to engineer all the numbers between 0 and 63, right? So I think, in fact, we can make all of the numbers. Let me jot that down for you. And so we can, in fact, make every number from 0 to 63. You have to think about it a little bit, right? You can try to maybe do a little quizzing here and ask yourself, well, how do I make, the number 7 or something like that? And you say, oh, okay, 7, let's see. So maybe that looks like 7, right? 4 plus 2 plus 1 is 7. Okay, so I won't bore you with all that playing around. But trust me and think about it a little bit. But you can actually make every single number, whole number, between 0 and 63 with these 6 bits. Okay, so the second question here asked, how many different numbers then can you make? And this is where you have to be a little bit smart, right? How many numbers are there between 0 and 63? Now the wrong answer is 63. Because I know it's tempting to say, well, you go up to 63, so it's 63. But since you can also make 0, it's actually 64. All right, so we can make numbers between 0 and 63. So we can actually make 64 different numbers. Or these numbers are sort of codes. Then I could make 64 different codes, you might say, with 6 bits of memory. Okay? Now you might notice something, and I'll say it while we're all here and together. 64, I didn't actually, I'll let you in on a secret. I didn't add up 63. I didn't add up these numbers to get 63. You could have. You could have said, what's 1 plus 2 plus 4 plus 8 plus 16 plus 32 in order to figure out how much 1111111 is. But actually, I think I used my brain a little bit and said, I think I should be able to make all of the numbers up to the next place value. So what's unique about 64, if you come back up here to my number, with 6 bits I could do all the place values, or that included the place values 1, 2, 4, 8, 16, 32. Well, what would the next place value have been if I went to the next one? Well, with 6 bits, right, 6, 1, 2, 3, 4, 5, 6, right, I stopped at 32. Right, that was with 6 bits. So what was the next number? If I had had a 7th one, it would have been the 64's place. And sure enough, how do I make the number 64? Is I would say, oh, in order to make the number 64, I think I need to do 1 there, and then 0, 0, 0, 0, 0, 0. In other words, I need 7 bits in order to do 64, which should hopefully maybe kind of make sense, because what that's saying is that if I put all 1s in my bits up here, which is how I made my number in the first place, right? If these are all, that's a little too big. Sorry. If I put all 1s up here, which is how I made my big number, that gives me 63. In other words, and we agreed I can make everything 0 to 63 with 6 bits. So I need the 7th bit, another one, basically it's saying I need to go to the next one in order to make the next number, which is 64. So there's sort of an interplay here, which I'll summarize for you on a future slide, that the number of number of bits is obviously very intimately tied with the range of numbers that you might be able to make, and it's also intimately tied with the place values themselves. Okay, so I'll summarize this all a little bit later. One last question that we have is, what if I needed to get 1,000 different codes? So from the last slide, we saw that we could get 64 different codes, namely the numbers 0 through 63, with 6 bits. So that's obviously not 1,000, right? That's not 1,000 different codes. So I'd need more in order to be able to do that. So how would I try to formulate an answer to this? Well, if I think about my place values, I'll draw some of them in here. So I got 1s and 2s and 4s and 8s and 16s, 32, 64. So I can't make, right, so the numbers that I can make, if I put 1, 1, 1, 1, 1 everywhere here, you can always get 1 less than the next place value. That's what we just saw in the last slide. So when I did 6 1s, 1, 2, 3, 4, 5, 6, that could make all the numbers between 0 and 63. So it's 1 less than the next place value. So if I need 1,000 different codes, I need to go much, much further in order to get, hopefully, reasonably close to 1,000. So let me keep going with my place values here. So I could do 128 is the next one. And then 256 is the next one. And I've run out of space, so I'm going to just sort of go above this. The next one would be 512. Now, if I did this number, so sorry that I've run out of space on you there, but I think you know what I mean. How much is that? Now, I could add that all up and say, okay, what's 512 plus 256 plus 128 and so on and so on. I could do that math. But if we're smart now and we can maybe use the analogy, well, the next place value would be 1024. And if we use our logic that we had on the last, that we noticed on the last slide, I think if I put all 1s, which is maxing it out, I should be able to get all the numbers from 0 to 1 less than the next place value. So either add up all of those ones, or I'm pretty sure this number that I just made up here is actually 1023. Okay? So maybe you just need to, maybe just to convince yourself of that, add it up maybe just one time. 512, 256, and so on and so on and so on. Add these guys all up. But I promise you will get 1 less than the next place value, which should be 1023. And just like in the last problem, I think I can make all the numbers between 0 and this, which means I think that would give me 1,000 different codes. Namely, I could just do the numbers 0 through 1,000, and with a few extra to spare. And how many bits do I have here? Let's see, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I think my summary here, right, is that maybe with 10 bits, we can make all the numbers 0 to 1023. And that, of course, does contain 1,000 different numbers or codes, if I'm thinking about these as some sort of a way of encoding something. I would need 10 bits, 10 blanks, or 10 zeros and ones in order to have 1,000 different codes. So you might imagine, a copy machine, and you're trying to come up with, which for whatever reason takes binary codes. If you have 1,000 employees and every employee needs to get a copy machine code that was going to be in binary, you would need to make them 10 digits long. You would need 10 bits in order to say, okay, everybody gets their own code. One of these numbers between 0 and 1023, you'd need 10 bits. 9 bits wouldn't do it. 9 bits, you could only get what you see in the bottom row here, that number, with 9 bits. And I don't even have to do the math. That number should be 511, because it's always 1 less than the next place value. That's not enough, right? 511 is not enough, or 512 is not enough. So I need to go to 1 more bit, right? So I would need 10 in this case. Again, there isn't necessarily a super awesome way of doing this. You're really just sort of asking yourself, what power of 2, 2 to the what, gets me to at least 1,000. And I don't know, there really isn't a super cute way to do that. You might just sort of start checking powers of 10. And I promise at some point when you type in 2 to the 9th power, that's not going to be enough. That's 512. But when you type in 2 to the 10th, you're going to get 1024. And you say, oh, okay, that means 10 bits should get me all of the numbers 0 to 1023. And that's 1024 different codes. Okay, so in case some of that wasn't clear, I'll just flash these through real quick. But there are some step-by-step, if you want, a wordier version of the process that we just did in order to do conversions. Here it is. So this is the second number that we did the conversion for, 10000011. If you really want to be official, I guess, about it, you might follow this routine. Put the number in a little chart like this. Put the place values, which are the powers of 2, maybe across the top. Write down in our world what these powers correspond to, right? 2 to the first, 2 and so on and so on. And then just sort of, and then in the last step, just say, well, how many of these do I have? And you can obviously skip all the zeros and add them up. And you should get the same number that we got, 131. I don't know that you really need to go through all the trouble of writing a chart, but if you feel happier doing that, by all means, you're welcome to do so. But I think that that's probably a little overkill. All right, so what are, just to try to summarize in a little bit of a better format, what's this sort of relationship that I hope we're maybe seeing? Yes, doing the number conversions is nice, and that's important. You'll see some homework questions where you have to do that. But the other big kind of piece is what we alluded to at the middle questions there, which is what do I get for a certain number of bits? So we discovered, hopefully, maybe 2 cute observations, and these are really important. I got to be honest, a lot of a lot of questions can probably be answered just by remembering these 2 facts that we saw when we did this. Depending on how many bits you have, right, however many bits you have, it's 2 to that number of bits is how many unique numbers or combinations or codes you can make with that many bits. So if you have 5 bits, you can make 2 to the 5th, which I think is 32, unique codes or unique combinations. Okay, so it's always 2 to the, which hopefully makes sense because it's base 2. And what are those codes? Well, you can make every number, so again, for how many bits you have, you can make every number between 0 and the largest number you can make, which is 2 to the number of bits minus 1. Okay, so again, with 5 bits, you can make the codes 0 to 2 to the 5th minus 1, which is 2 to the 5th is 32. So that would be 31. And hopefully this makes sense, right? So 5 bits gets you all the numbers 0 to 31, and there are 32 numbers in that range. Okay? And right? And so the next place value 2 to the 6th, I'm sorry, the next place value, right? The next place value is 32 if I write out 5 bits. So let me do that down here, right? So maybe third, if I call this 1, 2, 3, observation 1, observation 2, maybe just a sort of extra observation 3. With 5 bits, for example, what are the place values? 1, 2, 4, 8, 16. Right? With 5 bits, I can make 32 different numbers. I can make all the numbers 0 to 31, and maybe just one more observation. With 5 bits, the next place value, which isn't there, right? With 5 bits, I don't have that, right? I just have these guys. But if I did, right, the next number, the next bit would be 32, which hopefully you're now seeing plays a very important role because it's the answer to the first question, and 1 less than that is the answer to the second question. Okay, so there's a lot of cute tie-ins here, and I won't go too crazy with describing them to you. But I think that's these are 3 important things to kind of keep in mind. As you go through this, we're going to be asking questions more so like this: how many bits do you need in order to blah blah blah? More so than necessarily converting, just straight up converting binary to decimal and so forth. More so going to be interested in these types of questions. So mostly just try to keep this in mind. That it's 2 to the number of bits is the number of things you can make with n bits. So however many you have, you can make that many unique combinations. And again, it's every number between 0 and 1 less than that you could make. And I might also visualize that by saying, okay, if I started with however many bits, like 5, I can only go up to 31 because the next place value is 32, which I would get by doing 1 and then all zeros in these 5 bits. Okay, it's sort of the equivalent of when I say if I have 5 numbers in our system, I would say 99,999 is the biggest number I can make with 5 bits. In fact, I can make every number 0 through 99,999 in our world with 5 digits. But I would need a 6th one if I was to add one more, right? To go to just the next number. This is what we learned of carrying the 1. I would need to say, oh, now I need a 6th digit in order to do that, right? So one more. I can't do it. But I can make 100,000 different codes with 5 bits because I can do everything 0 through 99,999. Okay, so there's all these sort of cute little tie-ins, and it's exactly the same idea that we have in our number system, just base 2 instead of base 10. Okay, so the last thing we'll do in this video is just to go in reverse from the direction that we just did. And this is not much harder, but it does require maybe a little more care, I guess. So I'll step you through this one, and then I'll do one sort of from scratch at the very end here. So let's say I want to go the other way, and instead of taking a binary number and making it one of our numbers, I'm going to go the other way and take a decimal number, 245, and convert that to zeros and ones, convert that to a binary number. So it's a little trickier because you just have to sort of plan a little bit more when you're trying to figure out how to do this. So if I think about this and I say, all right, you can kind of, I know it's a lame example, but you can sort of think about this as saying, I have $245 to spend, and I'm going to try to distribute it to the base 2 place values, and I'm going to try to sort of spend and buy as much as I can at any given moment. So in order to know, well, how much can I afford, or what can I buy? I have $245. The first step is to maybe ask yourself, well, how far do I need to go? In other words, how many place values do I need? And for that, I want to say, well, where do I stop? What's the biggest place value? Obviously, I don't need a place value that's 1024, right? 1024 that we saw a few slides ago. I obviously don't need that digit because it's way more than 245. So I might just do a very simple thing, like try to draw out blanks until I at least get to 245, so I'll know where to stop. Okay, so I'm going to sort of sketch this out down here and say, all right, that's 1s and 2s and 4s and 8s and 16s and 32s and 64s and 128s and 256. Okay, so I think I can stop here for sure, because I know there's no way I'm going to have any 256s, because that's too much, right? It's already more than I can afford. So I can't have any 256s, so I think I could really stop with, I think that's 7. 1, 2, 3, 4, 5, 6, 7, 8, sorry. So I think I need 8 blanks, I guess I would say here, right? I would need all the first 8, so I need 1 byte. I need 1 byte of memory in order to do this. And another way of asking the question is to say, well, what's the power of 2? That is the largest number that's less than it, and it's 2 to the 7th, which is 128. So I should need 8 bits in order to code 245. So that's sort of step 1, is maybe just to draw out the blanks and cut yourself off, right? Say, okay, I can stop at the first time I get a place value that's above what I need. Okay, so either in a chart or just as I drew blanks, I think is probably sufficient, but we'll go with what the book has here and say, all right, draw out the place values of what you need. You need everything between 1 and the 128th place. Okay. And then you're kind of just telling yourself a little bit of a story here, where you're saying, okay, here's all the place values here. And then starting on the left, so start with the leftmost place value, which is 128. Now's where it's sort of telling yourself this sort of story of, I have money, I have $245, and I'm going to buy stuff with it. And I'm going to buy, if I can afford it, I'm going to buy the place values. So I start with the left and I say, all right, the first place value is it costs $128, and if I can afford that, I want to buy one. And I can, right? 128 I can afford. So I might do a little bit of side math here and say, I'm going to buy one of those and pay for it. And if I subtract here, that would leave me with $117. So, and I'm going to write a 1 down here because I bought one of those. Okay? And then I go to the next place value. So then I see things that are cost $64, and I say, can I afford that? Sure, I've got $117, so I can buy one of those too. Give me one of those. Okay, I'll keep telling the story. I go to the next place value, which is 32, and can I afford that? Yes. And if I subtract there, I'm left with $21, and I bought one, so put a 1 there. Okay, the next stuff is cost 16, and sure, I can afford that too. So buy one of those. But now when I get to the next place value, 8, I only got $5 left, so I can't buy any of those. So don't do it. Keep your $5. Now I get to the 4s, and so I put a 0 there to say I can't buy those. Now when I get to the 4s, sure, I can afford that. Buy one of those. But I only have $1 left, so I can't buy anything that costs $2. So put a 0 there, none of those. And then with my $1 that I have left, sure, when I get to the ones digit, I can buy one. And I'm broke now, I got no money. And I think if I've been a good person all along the way and keeping track of my digits, I think the number, the binary number that we see at the bottom here, 11110101, should be, hopefully, equal to our number, 245. So that's kind of the easiest way to do this. It's sort of a funny, I guess, routine in that it isn't just a formula to plug into. The easiest thing, to be honest, to do is just what we just did, which is to either tell yourself a cute story about your shopping and buying stuff, or, at the very least, do this. Now, you're never going to be able to buy two things. So I should have maybe said this as we were going through. Let me go back just real quickly to the first example when we started. Right, I had $245. I was never going to be able to buy two, right? So this cost, the first thing cost 128. Two of them would have been more money than I have. And actually, if you go through this whole problem, right, when I got to the next one, I had $117. Two of these would be too expensive. And nowhere in this shopping spree could I have ever actually afforded more than one. It was always either you can't afford any or you could buy one. And this is also sort of the beauty of the binary system, is that it's a good thing I couldn't afford two or three things, because remember, in the binary system, 2 and 3 and things like that don't exist. I either have none or one. And the good news is that this is exactly how the number turned out, and it should always turn out that way. All right? I should say, yes, right, maybe a reasonable thing for you to do when you get finished with the problem is to check it, right? So it's much easier to go from binary to decimal. So we got this answer when we were finished, 11110101, I think, right? So probably, especially if it's a test or something, or maybe even in the homework, it's probably not a bad idea to just do a quick, okay, how much is that? Does that add up to, 245 that we had a minute ago? And just do a quick double check to make sure it actually does add up. It's pretty easy, as you might imagine, to kind of mess this up, either just subtracting wrong or doing something kind of silly. So it's probably not a bad idea to double check yourself at the end of the problem. So let me just do one more for you so that I've done a little more to help you out here. And this is the last, and then this is the last slide. So let's see. So if I wanted to convert our number, 177, to binary, how might I do that? So my advice to you, like I said, is to maybe draw out blanks until you get to that number. So 1s, 2s, 4s, 8s, 16s, 32s, 64s, 128s, and I know the next one, which is 256, I know I'm not going to be able to afford that. 256. So I'm going to stop there with, that's also 8, I think, right? That's also 8 bytes. So, all right, so I think I'm ready to kind of go now. I'll try to maybe go a little faster than I did before. So I say, all right, I have $177 right now. And I'm going to start spending, start on the left and move to the right, and buy if you can, and don't buy if you can't. So the first thing I see is costs 128 bucks. So sure, give me one of those. And if I subtract, I think I get 49. All right, I get to 64 now, and I know I can't afford something for 64 bucks, so pass. I go to 32 and say, yep, I can afford something that's 32. That leaves me with $17. So then I go to 16 and I say, yep, I can buy one of them. And that leaves me with only $1. So I can't afford something that costs 8. I can't afford something that costs 4. I can't afford something that costs 0. My last dollar is spent on that last guy there. All right, and that, of course, that leaves me with nothing. And I think if I've done this right, the binary number should be right there in front of me now. So 10110001 should be the equivalent of our number, 177. And again, I should probably double check this at the end to make sure that I didn't do something wrong here. Okay, so try the homework problems and see what you make of them. I mean, in general, you should probably always be sort of having a piece of paper or several pieces of paper near you when you try these guys. But especially true, I think, with these problems because you're, legit having to do some math. So definitely have some paper with you so you're not trying to sort of do it all while you're looking at the screen. And a calculator is probably not a terrible idea either to have with you just to hopefully cut back on the number of maybe silly mistakes that you might make. But try these, which are problems, which are mainly converting back and forth between decimal and binary, and also jiving off of our observations about how many codes can I make, and what are the ranges of numbers and stuff like that.